Hey everyone, Mr. Cummings here, and welcome to this video on examples of inelastic collisions. So whenever we have a prompt or a problem, and that problem has a collision involved, the best first approach is going to be to assume that the collision is inelastic, or to not assume that it's elastic right away. Remember, elastic collisions are where the kinetic energy is conserved and the momentum is conserved, whereas an inelastic collision just means that the momentum is conserved. So we're going to start this problem, or any problems where we have a collision, by writing out the conservation of momentum equation for the scenario. And so we'll take a look at a couple examples here. So our first example is going to be a perfectly inelastic collision. This is where two objects are going to collide and they're going to stick. So we have a cart of 4m. It's traveling with a speed of v initial to the right. And then a second cart of mass 6m is traveling with a speed to the left of 2v0, so twice the speed. The carts collide and they stick together, and we want to find an expression for the final velocity. So we're going to visualize this with a drawing up top, where we just show exactly what's happening, and then we're going to work on solving it. So once again, we know from the context of this problem that the carts are going to collide, they're going to stick together, which tells us it's a perfectly inelastic collision. So we're going to use conservation of momentum. That still is true for all collisions and explosions. The difference here is when we write the terms for the final momentum of the system, we know that they share some final velocity vf. The carts are traveling together afterwards. So we'll have two separate terms for each momentum initial on the left-hand side of the equation. On the right-hand side, we're going to have the masses combined in parentheses multiplied by their shared velocity vf. So while we don't know the actual values of the masses and the velocities, we know their comparative masses and velocities. We know that ma is 4m, mb is 6m, va initial is going to be just v initial, and vb initial is going to be, we have to be careful here because it's moving left, it's going to be negative 2 v initial. So we're going to write these out in our bank, and then we're going to plug them into our equation and see what this does or how this helps us. So we see by plugging in all of these values for MAs and VA initials, what it's doing by writing out their relative velocities, or basically like what multiple they are of M or of V naught, it's putting everything in the same terms. So we're going to have an expression here that just has M's and V initials, and then one variable that we don't know, which is V final. So what we see by plugging in the masses for A and B and the velocities for A and B, it puts everything in the same terms, or the same or multiples of the same variables. So we have an m in every single term, so we get to cancel those out. All that's left on the left-hand side are something multiplied by v initial, and on the right-hand side, something multiplied by v final, which is what we're looking for. And so now we can rearrange this equation for v final and solve for vf in terms of v initial, which we'll do now. So we get that our final velocity is going to be negative 8 over 10, or 8 tenths, multiplied by our initial velocity, which we can simplify. We can say the final velocity is negative 4/5 v initial, or we can just say the final velocity is negative 0.8 times v initial, or 80% of the initial velocity, but in the negative direction. So now we'll look at another example where we have another inelastic collision. This time we are going to give some numbers here and see if we can solve for a numerical answer. So we have two identical spheres and they both have the same mass, m initial, or m naught. And they're initially traveling towards each other and they have velocities. A is moving at 3 meters per second to the right and B is moving at 5 meters per second to the left. They are going to collide and they're going to bounce off of each other this time, meaning they're not going to stick together. This is not perfectly elastic. And VA is going to have some final velocity, negative 3.4. So we want to calculate the final velocity of sphere B after the collision. So our first step here is going to make a variable bank of all the information that the text gives us, but all consolidated in one place so we can refer to it. So we know since this is a collision problem, we want to go ahead and start with the conservation of linear momentum. So we're going to write out this equation for the two-sphere system. So we're going to have the initial momentum of sphere A and sphere B added together. That's going to be the left-hand side of the equation. And on the right-hand side, we're going to have the the final momentum of sphere A and sphere B added together. Now notice here, since the two spheres are identical and they have the same mass, m naught is in every single term, so we're going to cancel that out, and we're just going to be left with terms for the initial and final velocity of each object, which will make this problem a little bit easier to solve. So since we are looking for the velocity of sphere B, we're going to go ahead and rearrange this expression algebraically to solve or isolate the VBF variable, and then we will plug in our numbers. So we get that our expression for the final velocity of object B is VA initial plus VB initial minus VA final. We're going to plug in all of our numerical information now, including the appropriate signs because these are vector quantities. So plugging in everything and then simplifying down and doing the arithmetic, we get that the final velocity of object B is 1.4 meters per second in the positive direction, or in the rightward direction. So what we see here is after the collision, object A bounces backwards and is now traveling to the left, whereas object B bounces off object A and is now traveling to the right. And that's going to be it on this video going over examples of inelastic collision problems. Thanks for tuning in, and I'll see you next time.